Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. We were discussing about immiscible flow. More importantly, we are talking about relative permeability in case of two-phase flow. What we did in the last lecture was we said that the relative permeability would be a function of saturation, and we said that relative permeability ideally is a function of surface tension, contact angle and pore structure, and there are fundamental work done, but and one can see if they change this interfacial tension. So, relative permeability would be the curves will shift for a gas oil system, as I have reported here. However, this general trend is to do experiments and get an empirical fit of this relative permeability versus saturation curve. So, what we see here is these are typical mathematical expressions for relative permeability for wetting and non-wetting phase. You can see this is the relative permeability of the wetting phase and relative permeability of the non-wetting phase, and you can see there is empirical relation. This is considered proportional to S effective to the power 4. S effective is called reduced saturation, and this reduced saturation is defined as S minus SWI divided by 1 minus SWI. So, what essentially they are saying is that the saturation has a window, we said between 0 to 1, but what they are saying here is that it is not exactly the window of 0 to 1, rather it is a window of SWI and 1. This part anyway you can never achieve, this part, because this you can never go below SWI for a two-phase system. So, actually the window is between SWI and 1. So, that is why one got this reduced saturation, and further they have conducted this something called a drainable porosity. That means porosity which can be drained. So, that is called drainable porosity. The porosity which can be through which oil could be injected. The entire, say let us say I talk about last time you remember 150 ml, out of these 150 ml 50 ml is the pore volume. So, entire 50 ml is not drainable, entire 50 ml we cannot fill this entire 50 ml by oil. Apart there would always be, we have to keep the provision for interstitial water saturation, right. So, interstitial water would remain in some place, rest of it is drainable, rest of it can be filled by oil. So, then that is drained. So, that is why we have a drainable porosity, which is the actual porosity into 1 minus SWI. So, we basically we are working with this part of the porosity, the other part is practically closed for us, and similarly the saturation we are working with this effective saturation, because below SWI we cannot go ever. So, with this definition of phi effective, S effective, phi effective and S effective, the empirical relation that is suggested by the researcher Corey is Kr wetting is proportional to S effective to the power 4, and Kr non-wetting is proportional to this function of S effective. So, generally the trend here is one gets a plot like this. So, generate these data points by experiment, where this is Kr and here it is, let us say SW or S oil, and then fit a line through this, keeping these correlations in mind. Okay. So, these correlations are from empirically available. So, keeping these correlations in mind, these lines are fitted, and these lines are now considered further for predicting what would be the flow. Now, we are talking about only the linear flow, right, in one unidirectional flow, but we may work with a radial system. So, there They are also, but this we have for a radial system we have what, minus k del p del k by mu del p del r was the VR, right. So, here also this only this k would be changed by k into k relative permeability, and this pressure would change to that pressure of that particular phase. So, all these extensions will be done, but first we need to know what is this k. K is KKR, k is known, I mean k is the base permeability, but what is this KR, relative permeability. So, this KR one must know. So, generally it is an experiment is performed on that porous medium with the same liquid system, and then one can find out what is the relative permeability. Next, what we get into is, suppose we have a two-phase flow, and suppose we have a situation, I mean which is very common for a reservoir, is that there is, let us say we talk about a unidirectional flow. So, let us say we are talking about a core plug, and this core plug is at interstitial saturation. That means it is basically oil with some amount of what they call, there is in reservoir language they call it connate water. So, there is small amount of water inside, which is the minimum amount of water that has to remain, and rest is all oil. And then suppose the water is injected into this core. Okay, this Barclay-Leverett method is developed for flow of wetting phase into a core which is at the limiting saturation of non-wetting phase. That means it has highest amount of non-wetting phase present with bare minimum of wetting phase that has to be there. So, that is how the entire core is, that is the status, and then what is injected is the wetting phase only, and then there will be a production. So, we expect first it would be what it would produce, it cannot produce any wetting phase, because wetting phase inside it is all non-wetting phase with bare minimum of wetting phase which can never be displaced, right. That is what is called interstitial saturation. So, initially they will produce all non-wetting phase. So, if I inject non-wetting phase, so if we inject 100 milliliter per hour of water, I will produce 100 milliliter per hour of oil from the outlet. So, this will continue, and the water, I am injecting a water, so water front will travel through this. So, then at one point this water front will reach the outlet. So, then after water front reaches the outlet, from that point on we will be they will be producing water plus oil. So, till this time only oil will be produced. So, till this, say let us say this water is injected, so there would be water front traveling, but we need not have to assume that this would be water front means, say let us say if I look at the saturation at an in between time. Okay. So, I am talking about saturation of wetting phase. Okay. So, let us say the water that I have injected, the front that I have injected, it has come up to this location. Okay. So, the saturation that we will have here is, the saturation here it is all water at this phase. So, what would be the saturation here? It is all water being injected. So, only leaving out the residual oil which can never be pushed out from the core. There is a residual oil, right. Our concept was that if this is the pore, there would be some amount of oil always will be sitting at the center which we can never remove. And similarly, I mean when we inject water, and when we start injecting oil only, then oil will flow this pathway and this blob will grow and everything, but there is some amount of water, which will be remaining here, which we can never remove. So, this water is we are referring as interstitial saturation, and this oil we are talking about is the residual saturation. So now, and in between we are having either we can switch from all water flow to all oil flow, but always this phase remains. So now let us say this front has traveled up to this point. So here at this location the saturation would be this, we have to leave this part out. So it would be 1 minus S NW R. NW is non-weighting residual. Residual means these has to be there minimum. So let us say we write 0.15. So 0.15 saturation, that means 15% of the total pore volume will be the non-weighting phase will remain in there, which can never be pushed out. So that is a limiting value. So this 0.15 non-weighting phase saturation, that means the water phase saturation would be 1 minus 0.15, that means 0.85. So water saturation at this location, at the inlet phase, we are injecting only water, no oil is injected from this phase. So the phase will have the saturation which is 0.85, that means 1 minus 0.15. We cannot go beyond 0.85, that is the limit, because 0.15 of oil, 0.15 of non-weighting phase has to remain inside the porous plug. So this is the limit. On the other hand, what is the limit on this side? Let us say the front has traveled up to this point. So beyond that, what do we have? Beyond this, there has to be this saturation of, what is that? That is interstitial water saturation. That is the minimum water that one has to have inside the plug. You cannot go below this saturation. So that is another limit. Okay. So in between there would be some, so the in between water has traveled, so it pushed out some amount of oil. So now one can expect this kind of a plot like this. So this is the typical saturation profile I can think of when the front has traveled up to this point. Beyond this point, this is interstitial water saturation. That is the situation when we started. That is the saturation everywhere, but already I have produced from this part whatever is the oil that has already been produced at the outlet. So this would be the saturation profile in this case. If I look at the next instance when the front has traveled up to this place, so this would probably look like this. Then when the front reaches the outlet, it is probably look like this. The front has already reached in the water saturation. We are plotting water saturation. Then gradually the water saturation will go up at further time as time increases, and then if after I am flowing 20 pore volumes or 30, I mean after flowing several pore volumes, we will reach this entire plug will have the 1 minus SNWR. That means we say that this entire plug is now at residual saturation, residual non-weighting phase saturation. So that is, it is primarily water, and the minimum amount of non-weighting phase has to be there. So it is flat, it is all constant. So that would be after injecting 20 or 30 pore volumes. So initially it develops like this. Initially it was, to start with, it was like this. It was all everywhere. This was the saturation, SWI, and then started injecting water. So front has traveled up to this position, front has traveled up to this position, front has traveled till the outlet. This is gradually growing, and at the end this would be the saturation. So this is something, this is a conceptual understanding we have as far as the flow of two phases are concerned. Now if somebody tries to plot cumulative flow at this time, if somebody tries to plot a cumulative flow here, in that case one notes that if I plot pore volume of non-weighting phase, non-weighting phase produced, produced, and this axis is pore volume. I write PV, pore volume of waiting phase injected. So, pore volume of waiting, pore volume, I should say pore volumes, pore volumes. Pore volumes means, let us say I said that 150 ml is the size of the core from outside. Out of that, pore volume, the void volume is 50 ml. So, rest 100 volume is the solid volume. So, 50 ml is the void volume, and so porosity is 1/3. So, now out of that 50 ml, now 50 ml is the pore volume, it is called pore volume of that particular plug. Now, suppose I inject 300 milliliter. So, that means I have injected 300 divided by 50, which is 6. So, I have injected 6 pore volumes through the core. So, instead of calling it in milliliter, pore volume PV becomes a unit of volume. If somebody says I have injected let us say 25 milliliter. So, immediately the implication would be that I have injected 25 divided by 50, which is half pore volume. So, immediately it will occur to me that half pore volume if I have injected, I would have must have gone halfway down this plug. If I have injected 3/4 pore volume, then I must have travelled 3/4 down the plug. So, instead of calling it in milliliter, we will be referring it in the pore volume would be the unit of volume in this case. So, in this case, so if we look at pore volume of non-wetting phase produced and pore volume of wetting phase injected, I must note here that how much of pore volume of non-wetting phase can we produce? There is a limit to it. First of all, it has to be less than 1, because I have to start with the non-wetting phase was there. I mean, non-wetting phase I am not injecting anything. Non-wetting phase is what is there in the plug. So, only that is something which we are extracting. First of, and second thing is, that is the first thing. Second thing is that there is a limiting saturation which goes by the name residual saturation. So, we have to leave something called a residual saturation. So, that has to remain inside the core, that cannot be pushed out. So, pore volume of non-wetting phase, this limit, upper limit here is simply 1 minus S NWR, 1 minus S NWR, right. So, because that is the residual non-wetting saturation we have to keep. So, initially I had 1, I mean the out of 1 out of the oil that was present, I can produce, I mean I can produce oil, but that there is a limit to it. It has to be less than it has to be it has to be one has to keep this residual phase saturation. So, there is a limit to it, and as a matter of fact I think it should be not only 1 minus SNWR. To start with, it was not fully 1 pore volume. To start with, this was to start with we had SWI. So, SWI, so initially the oil that was present was 1 minus SWI, pore volume of oil was present, and SWI of wetting phase was present, 1 minus SWI of non-wetting phase was present, and out of that, so that was present, and at the end we have to leave, it is not necessarily this. We can simply, we have to leave this much of oil at the end. So, this much of oil has to be, so the pore volume if I look at, it is 1 minus S NWR. So, that is the limit. Okay. So, now if I look at initial part, when this front has not reached the outlet, till this front has not reached the outlet, till that time whatever wetting phase was injected, the same pore volume of non-wetting phase will be produced. Whatever wetting phase is injected, same non-wetting phase would be produced. So, it would be a 45-degree line. After the breakthrough, now you would be producing both wetting and non-wetting phase together. So, it will not be the amount of wetting phase injected and amount of wetting phase produced, they will not be equal. So, this will start turning like this and it will reach asymptotically to this limit. So, if we look at the pore volume of non-wetting phase produced and versus pore volume of wetting phase injected. Now, you can inject 20 pore volumes here, wetting phase there is no limit, but non-wetting phase there is a limit, because non-wetting phase is what is sitting there in the plug, that is only produced, and it will follow a line like this, follow a trend like this. Now, suppose somebody wants to predict this behavior, somebody wants to predict this behavior of wetting and non-wetting phase. This would be the starting point. Obviously, if this is a simple situation, in the sense only we assume that it is we are injecting only the wetting phase. If we inject a mixture, there could be extension of this, and there are ways to handle additional complications, but this would be the starting point of two phase flow. So, here in this case, in this treatment, we have a very well known theory which goes by the name the Barclay-Leverett method. In case of Barclay-Leverett method, there is an important term here we must define, which is called FW. FW is fraction of flowing stream comprising of displacing fluid, which is the wetting phase, or in this case water. So, fraction of flowing stream comprising of displacing fluid. So, this is defined as QW by QT. So, if the total flow is QT and QW is the, out of that the QW is the fraction of water. So, you can see this FW can be approximated as fractional flow function. Fractional flow function is K relative permeability by mu for the wetting phase divided by K relative by mu wetting plus K relative by mu non-wetting. Why is it happening this way? You K, let's say, what are the other terms you have? K delta P by L, they are assuming same delta P here, and here also this would be KKR delta P by L, KKR delta P by L. So, with this assumption, cancelling these terms altogether, one can come up with FW, the fractional flow function, which is, so this gives me, when I multiply this Kr mu K delta P by L, this gives me the superficial velocity or volumetric flux of wetting phase divided by volumetric flux of wetting phase plus volumetric flux of non-wetting phase. So, this is basically same as QW by QT, QW by QW plus QNW. So, that is QW by QT. So, this FW can be approximated by fractional flow function, which is Kr by mu wetting by Kr by mu wetting and Kr by mu non-wetting. And Kr as a function of saturation, we have already said that we can do some experiment there, plot Kr versus saturation, and then we can generate data points, and we have some correlation. For example, Corey's expression is there, how relative permeability depends on saturation. So, those kind of expressions can be fitted to find out an expression for relative permeability. So, if we have, so basically this FW will depend on, see, these are all constants, mu of wetting phase, mu of non-wetting phase, these are constant. And if I say that Kr for a particular system depends on saturation, SW, or I mean Kr is a function of saturation. So, this Kr is for wetting phase, this Kr is for non-wetting phase here. So, these Kr, so then entire thing we can write Fw for a particular system. Fw is a function of saturation. Okay, let us say water saturation. So, Fw is a function of SW. So, FW can be, so one can find out by looking at these correlations that one get different data points and fit it with some expression. So, one can come up with some FW expression for FW as a function of saturation. And further, what one can do in this regard is one can do a material balance over an infinitesimal element. That means that one can have one can draw a material balance. That means, suppose this is the core. If one picks up a differential length dx, let us say one picks up a differential length dx, and they say that what is the flow that is taking place here? Here the flow is Qt. So, Qt is the volumetric flow rate, this divided by area, this gives me volumetric flux. Okay. So, that is the flow of Qt is equal to Qw, because I am only having flow of no, this say for example, one particular differential element. So, we have a flow of Qt here, then we have here we can write flow in minus flow out would be the accumulation in this differential element. So, accumulation in the sense here in this case, since it is an incompressible system, the only accumulation can take place is the change in water saturation. Okay. So, a part that was SW, now after time delta t we find that there is a change in water saturation, which is, let us say, delta SW. So, delta SW is the change in saturation. So, that is the only how the only accumulation can take place. So, what is the volume of this element? dx into A is the volume, overall volume, multiplied by porosity is the pore volume, multiplied by delta SW, that is the change in saturation. Okay. So, this would be the change in volume of water as far as this differential element is concerned. Okay. So, change in volume of water as far as this differential element is concerned, and this has to be equal to this is basically the accumulation of water in that case. This has to be the Qw volumetric flow of water, volumetric flow rate multiplied by, so volumetric flow rate at x. Okay. Volumetric flow rate. So, let us say this is delta SW, this is there. Actually, you should not be writing it as dx, we should be writing it as delta x. So, delta x A phi delta SW, that has to be the volumetric flow rate at x. This is x. So, at x volumetric flow rate over time delta t, over duration delta t, minus the volumetric flow rate that has left, x plus delta x over time delta t. So, when we take this and further this Qw on the right hand side, so this is equal to Qw on the right hand side can be replaced by Fw into Qt. We can see Fw into Qt, Qw is equal to Fw into Qt at x, sorry, Qt is constant, Qt is not changing. So, we should be writing it as Fw at x Qt delta t minus Fw at x plus delta x and x plus delta x Qt delta t. So, now if you take this delta t to the left hand side, so delta SW divided by delta t tending to 0, this gives me del SW del t at constant x, and on the right hand side, QW at x minus QW at x plus delta x divided by this delta x, this gives me, now QW is basically QT into a, QT comes out, QT is the constant, so QT comes out, so this becomes FW at x minus FW at x plus delta x divided by this delta x, limit delta x tending to 0. So, this gives me del FW del x at constant t, and outside you have QT here, and this phi into a goes to the right hand side. So, from this equation, one can arrive at this material balance. So, essentially this is a material balance we have, this is the FW expression for FW we have. So, we will build on this. This Buckley-Leverett method works with this basic equation with the definition of FW. So, we will build on this in the next lecture, how Buckley-Leverett method can be used for to predict, for example, the cumulative flow that I presented, or the saturation profile over the length of the porous plug that I presented in the next lecture. Thank you very much.